Welcome to the Explainer, everyone. Today we're going to dive into a concept that's pretty much the bedrock for everything from graphing to modern databases, the Cartesian product. And the way we're going to master it is by working through a classic math exercise, just breaking it down step by step. Okay, so first up, we've got a little puzzle for you. Now, this might look like a regular old algebra problem, but here's the thing. The one simple rule you need to solve this, it's literally the master key to this entire topic. If you get this, you're going to get everything else. So here's our game plan for today. We're going to start with the absolute basics. What's an ordered pair? Then we'll learn how to build sets with them, and even how to work backward to find the original sets. After that, we'll test our knowledge, and finally, we'll tie it all together to see why this stuff is actually so important. So let's jump right into our first section. To crack that opening puzzle, you only need to know one super simple rule about what it means for two of these ordered pairs to be equal. And here it is, the big secret. For two ordered pairs to be equal, their first parts have to be equal, and their second parts have to be equal. That's it. So that one rule lets us take that complicated-looking equation and split it into two really simple ones. We just solve the first one for x, solve the second one for y, and boom, we're done. That idea is the foundation for everything we're about to do.
All right, so we've totally nailed the atom of this whole thing, the ordered pair. Now let's see how we can use these little building blocks to create much bigger, more interesting structures by combining entire sets together.
You know, the first rule of building anything is knowing how big it's going to be, right? Well, lucky for us, it's just simple multiplication. So, if your first set, set A, has 3 elements, and your second set, set B, also has 3 elements, just like in problem 2, then the Cartesian product of the two is always going to have 3 times 3, which is, of course, 9 elements. Easy as that.
So how do we actually make all these pairs? Well, it's a really systematic process. You just take the first element from the first set, G, in this case the number 7, and you pair it up with every single element in H. That gives you 7, 5, 7, 4, and 7, 2. Then you just do the same thing with the next element from G, the number 8, and there you have it. That's the whole set.
Now, this is where it gets really interesting. What happens if we flip the order and do H cross G instead? Bam! You get a totally different set of pairs. Remember our rule from the beginning? The ordered pair 7, 5 is not the same thing as 5, 7, and this shows us something absolutely crucial. When it comes to Cartesian products, order matters a lot. Okay, so this leads us to the next logical question, right? We know how to build the final product if we have the original sets. But what if it's the other way around? What if someone just gives you the final product set? How do you reverse engineer it to find the original pieces?
And you're going to love this, because the rule for working backward is incredibly simple. There's no fancy formula. To get the first original set, you literally just grab all the unique first numbers from every pair. And to get the second set, you guessed it, you just collect all the unique second numbers. It's really just a sorting game.
So let's put that to the test with problem 6 here. If we look at all the first elements in the pairs, what do we see? We see A, B, and B. The unique ones are just A and B. That's our set A. Now for the second elements, X, Y, X, and Y. The unique ones are just X and Y, and there you go, that's set B. Done.
And what's cool is this logic works even if you're only given a sample of the final product. In this problem, we can see the first elements are X, Y, and Z. The problem tells us set A is supposed to have 3 elements, so that has to be our set A. For the second elements, we see a 1 and a 2, and since set B is supposed to have 2 elements, that must be it. We just reconstructed the whole thing from just a few clues.
All right, now for a proper challenge. Problem 10. We're told that A cross A has 9 elements, but we're only given 2 of them, -1, 0 and 0, 1. Well, just from those 2 pairs, we can deduce that the numbers -1, 0, and 1 must all be in set A. We also know that the total number of elements is 9, and the only way to get 9 by multiplying a number by itself is 3 times 3. So set A must have 3 elements. Therefore, set A has to be -1, 0, 1. And once we know that, we can easily figure out the other 7 missing pairs.
Fantastic. We've built them, we've taken them apart, now it's time to put our knowledge to the test. We're going to look at a few true or false statements that will really check if we've gotten a little details right.
All right, check this out. From problem 4, is this statement true or false? Take a quick second and think back to what we learned about how many elements the final product set is supposed to have.
It's false, and here's why. Set P has 2 elements, and set Q has 2 elements, so their product must have 2 times 2, which is 4 elements. The statement is missing two pairs, m, m and n, n. The correct full set is the one you see right here.
Now, the other two statements here are actually true. The first one, well, that's just the official textbook definition of what we've been doing this whole time. The second one is also true, and it makes perfect sense if you think about it. First, you find the intersection of set B and the empty set, which is of course just the empty set. Then you try to make a Cartesian product with set A and that empty set. But since there's nothing in the second set to make pairs with, the result is also empty.
Okay, we've covered a ton of ground here. We've built sets, broken them down, tested the rules. So what's the big deal? Why does any of this really matter? Why is this one idea so powerful in mathematics?
Let's go back to problem 8 for a second. We have two very simple sets, A and B. When we create the Cartesian product, A cross B, we get this set of 4 ordered pairs. What this new set really is a complete list of every single possible way you can connect an element from A to an element from B. It is the entire universe of all possible connections between them.
But here's where things get really cool. Let's forget about the individual pairs for a moment. Instead, think about this. How many different groups of these pairs can we possibly make? In other words, how many different subsets can we form from this new collection of 4 pairs?
The answer is 16. And the rule for this is actually so elegant and simple. If a set has n elements, it will always have 2 to the power of n possible subsets. In our case, our set A cross B has 4 elements, so it has 2 to the power of 4, or 16 different subsets.
And these subsets can be literally any combination you can think of. It could be the empty set with none of the pairs. It could be a subset that has just one specific pairing in it. It could be a random combination of a few of them, or it could be the entire original set itself. Every single one of these 16 possibilities is a valid subset, and each of them has a very special name.
Each one of those 16 subsets is formally called a relation. And this is the big idea, the main takeaway. The Cartesian product isn't the end of the story, it's just the beginning. It creates the entire universe of all possible connections. And a relation is simply us choosing a specific group of those connections that we actually care about for some reason.
And this leaves us with a final and incredibly powerful question. We've learned how to generate every single possible pairing between two sets. But what happens when we start being selective? What happens when we decide to only choose the pairs that actually matter for a specific purpose? Well, it turns out that by learning how to choose specific subsets, these specific relations, we unlock the power to describe everything from mathematical functions to the entire structure of databases. And that is exactly where we're headed next.